Hello again, everybody. Welcome back. Today we're going to be starting Chapter 8, starting with Section 8.1, which is all about polar coordinates. This chapter is actually pretty cool. We get to learn a whole new coordinate system. Then we're going to get a total, complete exploration of complex numbers, including the complex plane, which is really cool. And then at the end, we're going to talk about vectors and the dot product and the cross product. But to begin, let's learn about polar coordinates. All right, so this is section 8.1, and this is the overview. So we're going to briefly review the idea of coordinate systems and the Cartesian coordinate system, which all of you are very familiar with, I'm sure. Then we're going to develop the polar coordinate system, talk about how to convert between systems, and then, actually, you know what? These last 2 points here, polar curves and symmetry, we're going to save those for the next section, if I'm not mistaken. Let me double check here. Do, 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 do. Yeah, we're going to save those for the next section. So we'll just talk about the first 4 bullet points here and leave polar curves for the next section. All right, so first, what is a coordinate system? So in geometry, a coordinate system is just a system that uses one or more numbers, which we call coordinates, to uniquely determine the position of the points or other geometric elements on a manifold, such as Euclidean space. So this is the very general definition of a coordinate system. And you don't really need to know what manifolds are in this class, but the idea here is that Euclidean space, which is the space that you've been working with since you were a kid, it's a manifold. So these ideas you can actually generalize to things that are different than Euclidean space, which some of you are going to see later on in your careers. But the main idea is that we're going to use one or more numbers to determine the location of a point. That's really what it is. Okay, so far we've been using one coordinate system, and this is what you've been using for your entire math education. That's called the Cartesian coordinate system or the rectangular coordinate system. So this is the one with the XY plane, right? Where there's an X coordinate and a Y coordinate. This is something you're very familiar with. There are actually many, many different coordinate systems, and some are easier to use than others. It really just depends on the context. And that's one of the reasons we're going to learn a new one today. So in this section, we're going to learn about a new coordinate system called the polar coordinate system. And this system is actually going to come back in a really big way in Calc 2. So I'm glad that you all are getting a complete exploration of this idea in this class, because it's going to prepare you very well when it comes back again in Calc 2. When you get to Calc 3, you're going to learn about two other coordinate systems, the cylindrical coordinate system and the spherical coordinate system. And again, the idea is we're just going to use some numbers, some coordinates to determine the location of some points. That's the idea. All right, so a brief review. This is the Cartesian coordinate system. What does the Cartesian coordinate system do? It uses the ordered pair x comma y to uniquely to uniquely determine the location of a point in the plane. The plane is denoted by this symbol, r squared, because it's r cross r. Basically, it just means it's almost like r times r. It's two real lines crossing right at the middle, the origin right here. So the idea is that you can determine the location of any point on the xy plane by just listing its x coordinate and its y coordinate in that order. So for example, the point P right here is given by the coordinates a comma b. What is A? A is this horizontal displacement from the origin, and B is the vertical displacement from the origin. And so when you track those two coordinates, it'll give you the exact location of this point. And we can say that this point is at the location A comma B. And that's really what it is. So you've seen this idea a lot. We're just kind of reviewing it. The axes cross or meet at a point called the origin, and that point has the coordinates 0, comma 0. That's essentially like where the two real lines cross over each other. And yeah, so the idea is this. The location of any point on the plane can be described in this way. So if you want to point your finger at any point on that plane, I can tell you the coordinates of that point, and we'll be able to talk about them in that way, or talk about it in that way. All right, so that's the Cartesian coordinate system. Now let's talk about the polar coordinate system. So the polar coordinate system still uses an ordered pair, but now the ordered pair is of this form, r comma theta. It's still doing the same thing. It's going to uniquely determine the location of a point, but in this case, r is the radius of a circle, and theta is the angle between a ray and the polar axis. Polar axis. So this is the general picture right here. The idea is that you pick any point on the plane. So maybe we'll do this one right here. Here's a point that you picked on this screen, and you want to describe the location of that point. Well, the way that we're going to describe it is we know that that point lies on a circle of radius r that is centered at the origin. So something like this. Okay, pretend that's a perfect circle, right? So the radius of that circle is here, and it has length r. So when we give the value of r, we are giving the radius of a circle on which this point lies. That's the idea. So that point lies somewhere on that circle. Then we need a second coordinate to determine the exact location of that point on the circle. And in that case, it's going to be the angle theta right here. So the angle theta tells us how much to tip upward from the x-axis to get to that point, right? So the polar axis here coincides with the x-axis in the standard Cartesian coordinate system. So if I were to like overlay the two systems, it would look like this, x and y. Oops, there we go, y. So it's the same thing that we've seen before when we were first developing trigonometry, right? Literally back in section, oh geez, what was it? 5.2, I think, 5.1 or 5.2. And we would center this angle in standard position, which meant at the origin of the Cartesian coordinate system. So we're still doing the same thing here, but now instead of describing the point in terms of x's and y's, we're describing it in terms of r's and thetas, radiuses and angles. That's the idea. Okay. Um, Now, the ray that represents the polar axis typically coincides with the positive x-axis. That's what I was just saying a moment ago. And the point r comma theta gives the polar coordinates of a point. So this is basically the entire thing right here. These are the polar coordinates of a point. And again, any point in the plane can be described this way. So if you put your finger on any point in the plane, see, pretend this is like a point that you pick in the plane. Well, I can tell you the radius of a circle, maybe we'll call that one R2, the radius of a circle where that point lies on the circle. And then I can tell you this angle here, maybe I'll call it theta. So now I can say that this point is at the coordinates R2 comma alpha, sorry, what am I saying, theta? Alpha. And that's really the idea. So not too bad, right? Not too bad. We're going to get to see some really, really cool stuff with this because one of the things I always say is you should be asking, like, why do I care about this? What's the point of this? What do we gain by doing this? What's the purpose behind all of this? You know, make meaning, make sense of it. We're going to see that a lot, especially in the next section. So one of the cool things about polar coordinates that's a little bit different than what we've seen before is that we can extend the meaning of the coordinates r comma theta to negative radii by taking negative r to mean the ray that is reflected through the origin. So what I mean here is you can have a negative first coordinate. For example, you could say that r is equal to -2, and that would still have meaning in this coordinate system, the polar coordinate system. And the way that we define it is if this point is r comma theta, then negative r comma theta would basically be reflecting this ray. Let me use blue here, or no, better yet, I'll use red or something. It would be taking this ray that I'm sketching here, the red ray, and reflecting it through the origin so that you end up with this ray over here instead. And this would lead you to the point negative r comma theta. So that's what a negative value will be. Oh, hold on one second. I just realized. Ah, there we go. My computer wasn't plugged in. It was about to die on me. Okay, so where was I? Oh yeah, that's right. So another way of describing this reflected point precisely is that this point is the same thing as taking your point r comma theta and adding pi to the angle theta. And we're going to see some examples of this in just a minute, but this is the same thing. So what this really means is that the point r comma theta is equal to the point, what's it going to be? Oh, I always mess this up when I'm trying to do it on the fly. Negative r comma theta plus pi. Oops, sorry, that there should be a plus in there. Plus pi. That's right. Because if I were to reflect the radius and then add, yes, that's right. There we go. That's the idea. That's the idea. Okay, so let's do some examples. So let's just plot these points in the Cartesian coordinate plane, the Cartesian coordinate system. Um, oh, you know what? I just realized I forgot to include a negative radius. So we're going to tweak that a little bit, and I'll change it on the slides later. I think what I'm going to use for a negative radius, let's do, how about this one right here? Let's alter E, and I'll change it later on the slides. Let's make the radius for this one negative 1/2 instead, negative 1/2, and we'll get to that. So let's just plot all these points. Let's look at A first. So we're going to plot the point 1 comma 5 pi over 4. And remember, these all have the structure r comma theta, r comma theta. So we're being given a radius and then an angle. And in this case, the radius is 1. So we're going to lie on a circle of radius 1. And the angle that we're going to sweep out from the polar axis is 5 pi over 4. So let's see what that one looks like. Here we go. This is where that point lies. So this is the coordinate, or sorry, this is the point 1 comma 5 pi over 4 given in polar coordinates. And it makes sense once you kind of see the picture, right? So this right here, this is the polar plane, or in this case, what we're looking at is a polar grid. And what I marked on this grid are all of the standard angles. So like pi over 6, pi over 4, pi over 3, pi over 2, and all their multiples in all their multiples that are less than 2 pi. So this is like a polar grid. And what you can see is you can see all of the concentric circles of the different radii. So that's what we've got right here. If you look at like here, that's a circle of radius 1. This is a circle of radius 2. And our point lies on a circle of radius 1. So we're going to be on this circle right here, centered at the origin. And we're going to sweep around an angle of 5 pi over 4. So here's the polar axis, and we're going to go around 5 pi over 4 radians, and then that'll land us at the point. There it is. And that's pretty much it. That's pretty much it. So hopefully that's not too bad. You can do this not without too much trouble, right? You just got to remember it's a radius and an angle. Okay, so let's take a look at this point, 2 comma 3 pi. Now we're lying on a circle of radius 2, so we're out here. Oops, sorry. And we're going around an angle of 3 pi. So what's 3 pi? We're going to go around this way and then this way. That's 3 pi. There we go. And that's the point. Okay, let's look at the next one. This is the one where the circle has radius 2 and the angle is negative. So you can still have negative angles. Negative 2 pi over 3, that's like going this way clockwise, right? And we're going to lie on the circle of radius 2. And so that's how we can locate a point. And again, you should just let your mind go wild with this stuff. This can describe any point anywhere on the plane. You just give the radius, basically the distance from the origin, and you give the angle that we would need to rotate around, to get to that point. Okay, what about pi comma 15 degrees? So the reason I put this one on here is because you do got to remember that these are ordered pairs, which means the order matters. So you can't just exchange the location of r and theta willy-nilly. So here, this is r, and this is theta. It's all right for our radius to be pi. That's okay. The radius doesn't have to be some whole number or just some like integer or something like that. It could be any real number. You just got to remember that the first coordinate is the radius and the second coordinate is the angle. So here we're going to lie on a circle of radius pi. Pi is a little bit bigger than 3, and so that's why we're lying on the circle that kind of has this radius right here. Can't draw it very well. There we go. So it's a little bit bigger than 3. The radius is a little bit bigger than 3, about 0.141592 bigger than 3. Okay, then our angle is negative 15 degrees. So we're just going to tip downward, tip downward 15 degrees. And there we go. That's the idea. Okay, now I think let's do, okay, so this is the one that where I wanted to use a negative radius. So we're going to alter the question that you see here on the slides to be negative 1/2 4 pi over 3. And the way that you can draw this type of thing is the radius is going to be negative, but if we mark out the angle 4 pi over 3 first, and then we find where that point is on the circle with the positive radius, then we can just reflect that point through the origin to get the actual location. So I'm going to zoom in a little bit here. Here we go. So currently, the point that is plotted right here is the point 1/2 comma 4 pi over 3, right? So the radius is positive. We've circled around 4 pi over 3 radians, and we're on a circle of radius 1/2. Now, if I want to plot the point negative 1/2 comma 4 pi over 3, what that means is negative 1/2 comma 4 pi over 3. That means we're going to circle around by that same angle, but now the radius is going to be negative, so it's going to literally pass us through the origin up to here. So this would be the point negative 1/2 comma 4 pi over 3. That's the point right there. So the way that I always remember this is basically if you mark out the angle and then you pretend the radius is positive, you can basically just reflect through the origin to find the location of the point with the negative radius. This also brings me to another point, which I think I ask in another set. Oh yeah, there it is, in another slide. Just like in the Cartesian coordinate system, there are infinitely many representations of a point. And I'll show you an example in just a sec. But it's a little bit easier to see in the polar coordinate system. So look at this right here. Maybe some of you were thinking this too. If this is the point negative 1/2 comma 4 pi over 3, some of you might have been asking, well, wait, couldn't I just describe that point as 1/2 comma pi over 3? And the answer is yes, you could. These 2 points are equal. So this point is equal to the point 1/2 comma pi over 3. And that's actually the relationship I had written on an earlier slide, actually, up in the upper right-hand corner, right? It was like r comma theta equals negative r comma theta plus pi. And that's what this is. So every single point on the plane has infinitely many representations in polar coordinates. And this is something that you may not have thought about explicitly with the Cartesian plane, but it's the same for the Cartesian plane. Let me give you a quick example. Let me draw the Cartesian plane here. Okay, so here's xy, Cartesian plane. So now we're working in Cartesian coordinates. Let's look at the point, let's call it 1 comma 3. All right, so this is one way of representing that point, 1 comma 3. So this would be 1, this would be 3. There's another way to represent it. It might seem like cheating, but it's not. I could write it as 2 over 2 comma 6 over 2. That's another way of describing the point. 2 over 2 is equal to 1, 6 over 2 is equal to 3, so there's another representation of that point. Or I could even say that this is the same as, maybe we'll do 4 over 4, comma 18 over 6. Well, that's equivalent to 1 comma 3. So those points, or those representations, are all describing the same point. There you go. So not so weird. It's not so weird that every point has these infinitely many representations. Okay, and then there was one more right here. So once again, the reason that I wanted to put this question on here is because you've got to remember that this is your radius and this is your angle theta. That's your angle theta. Oh, and again, remember that we're assuming the angle is in terms of radians, unless it's explicitly stated that it's in degrees using the little degree symbol. So here we've got a circle of radius E. E is about 2.717. And our angle theta is 2 radians. 2 radians. So here's the radius of our circle. There you go. Notice that it's about 2.717. It's almost 3, but it's less than 3. And then 2 radians is this angle right here. Oops. This is 2 radians. And that's it. That's the whole idea. Plot, there you go. So now we can see how to plot these points. You'll get a lot more practice on the homework, and you can honestly just practice anytime you want. Just think about how you would convert, right? And we're going to see how to convert in just a moment. So let's try this one. See if you can do this one on your own. I'll give you a couple minutes here. Let's say we have the point 2 comma pi over 3. See if you can find 2 other equivalent representations in polar coordinates, one with a positive radius and one with a negative radius. So first, just think about how you would do that. All right, now just say anything out loud to yourself about how you would do that, just to give your brain that feedback. All right, now try to do it yourself. See if you can plot these points and then give 2 other representations, one with radius positive and one with radius negative. All right, now let's do it together. For me, I'm a pretty visual learner, so if I can draw a picture of something, I usually will. And in this case, I'm going to draw a picture just to give myself something to help me make sense of what these points are going to look like, these different representations. So let's plot the point 2 comma pi over 3 first. I'm going to draw this, and let's see, I'll say this is 1, this is 2, so I've got a circle of radius 2. Use my technology to my advantage here. Um, okay, now pi over 3 is this angle right here. I'll erase this so it's not too confusing. There we go. Okay, so this is the point 2 comma pi over 3. All right, now let's find 2 other representations with the radius positive first. So basically, how else could I describe this point where I'm going to keep the radius of 2, but I need to find another angle that will land me at the same location? Maybe you can kind of think of it in your head. Uh, I can just add 2 pi, right? So if I go around the circle again by 2 pi, I'm going to land at the same point. So I just need to do 2 pi plus pi over 3. Let's see, so what is that? 2 pi? 2 pi is 6 pi over 3, so we're going to have 7 pi over 3. There we go. That's right, yeah, 7 pi over 3. And then I could do it again, right? I could go around the circle again. Radius is still 2, but now I'm going to add another, what is it, 6 pi over 3 to that, so I should get 13 pi over 3. There we go. All right, so those are 2 other representations of that point with the radius positive. Now let's do the same thing, but we want the radius to be negative in this case. So remember, if you have a negative radius, it reflects you through the origin, or I should say through the origin. So this point that we're looking at, 2 comma pi over 3, if I were to reflect it through the origin, I'd have a negative radius. So down here, this point, this is the point negative, I'm sorry, yeah, negative 2 comma pi over 3. There we go. But, but that's the point that's reflected, right? What I want to do is I want to find a point that's equivalent to the one that I started with, that's equivalent to this one. So I know that the radius is going to be negative 2, but now I need to change the angle. So how do I get an angle that's going to land me back there? Well, if you remember, we can just add pi, right? Add pi to our angle and that'll work. So I'm going to do this. Come back up here. This is also equal to the point negative 2 comma 4 pi over 3. 4 pi over 3. And I mean the point that's in orange, the point that we started with. And to see why that's going to be true, let me draw it this way. Let me get rid of this. Okay, so let's mark 4 pi over 3 first. If I mark 4 pi over 3, it's right down here. That's 4 pi over 3. And in fact, this is the point, this will be the point 2 comma 4 pi over 3. There we go. Now if I change the angle, I'm sorry, now if I change the radius to be negative 2, it's going to reflect me through the origin back to the point that I'm interested in. So there we go. negative 2 comma 4 pi over 3. And then if I want another representation, I can just add 2 pi to that again. So negative 2 comma, okay, so that's going to be 6 pi over 3, so 10 pi over 3. And there we go. That's how you can do it. So once again, you're always going back to these circles. You're thinking about angles, standard angles, adding pi, adding 2 pi. These are all skills that you've got earlier in the course. So it's really nice that it all kind of builds up. All right. Here's some other examples here. Oh yeah, in this case, I even used a negative angle. So again, there's many other ways to do it. Lots and lots of different ways to do it. I think I had this one, but I did not have this one. This one I wanted to use a negative angle, it looks like. All right, so now the next question is, we've got this new coordinate system. How do I convert between the two? How do I convert from Cartesian to polar and from polar to Cartesian, right? So to talk about that, we've got to get the definition of a high-minded concept, you could say, what an isomorphism is. So an isomorphism is a structure-preserving mapping between two structures of the same type that can be reversed by an inverse mapping. Oof. Okay, that's a mouthful, right? I'm pretty sure none of you or not many of you have heard of this before, but this is something that some of you are going to study a lot more later on. And there's some key ideas here. So it's a structure preserving mapping between two structures of the same type that can be reversed by an inverse mapping. That's an isomorphism. And what we're saying here, and what we've been kind of hinting at for the whole lesson, is that the Cartesian coordinate system and the polar coordinate system are isomorphic. So in essence, they're describing the same structure with different words. That's really what it is. So if the structure is not changing, but the words that we are using to describe it are changing, are there some other words that could pass us back and forth between the two descriptions? Or maybe I should say relationships. Are there specific relationships that can pass us between the two representations, like so? Yeah, there you go. Do there exist mappings between each system that let you convert back and forth? And perhaps some of you have been kind of thinking this or seeing it in the back of your head, but there are. And the isomorphism between these two coordinate systems is going to look very familiar. Here we go. So the isomorphism equations that'll let you convert from polar coordinates to Cartesian coordinates are these ones. X equals r cosine theta and y equals r sine theta. Ta-da! Those are the isomorphism equations. The isomorphism equations, if you want to convert the other way, if you want to convert from Cartesian to polar, they're given by these equations here. There we go. So basically, if you have Cartesian coordinates and you want to go to polar coordinates, these equations down here will let you find the radius, and it'll let you find the angle, just like so. So these are quite literally the formulas that allow us to map back and forth between these two coordinate systems. So these are the isomorphism equations. And what does the picture look like? The picture looks just like one you have seen for a long time. This one right here. This one right here. At least for this course, right? So remember, what is this distance? That's the horizontal displacement, which we called cosine. And if our radius is 1, then x would just be cosine theta. But since our radius is r, x is going to be r cosine theta. Same thing on the vertical part here, right? This vertical displacement, we were calling it sine of theta. And if our radius was 1, that would just be sine of theta. But because it's r, it's going to be r sine of theta. And that's pretty much it. So if you've got those equations, you can convert back and forth between Cartesian and polar. That's the relationship. That's the isomorphism. Let's practice. Let's try it. Let's convert this to Cartesian coordinates. And this is one that I want you to try out on your own before we do it together. So think about how you would do this and see if you can just remember the equations having glanced at them a moment ago. All right, now say something out loud. Maybe say what the equations are going to be. Which equations are you going to use to convert? All right, now try to convert it. So see if you can get this polar coordinate, or this point given in polar coordinates, to a point given in Cartesian coordinates, and then we'll do it together. All right, here we go. So we're given the radius and we're given the angle, and what we need to find is x and y. But we know the isomorphism equations. X equals r cosine theta. So for us, that's going to be 2 times cosine of pi over 6. Pi over 6 is one of the standard angles, and cosine is root 3 over 2. So this is going to be 2 times root 3 over 2, which is root 3. That's the x coordinate of our point. Now let's do the same for y. Y equals r sine of theta, which is 2 times sine of pi over 6, which is 2 times 1/2, which is 1. So in Cartesian coordinates, this is the point root 3 comma 1. And now that's how we convert. There we go. Oh wait, did I? Oh, you know what? I apologize. My radius is not 2. My radius is 3. This is why you got to work in groups, right? So I apologize. Okay, these 2's should be 3's, and that'll change the result here. That's a 3, that's a 3, that's a 3. So 3 root 3 over 2, and 3 over 2. There we go. That's the point. So that's the point 3 comma pi over 6 written in Cartesian form. So this is polar, and this is Cartesian. All right, now let's try to go the other way. So let's do another example. See if you can convert this point to polar coordinates. So just like before, think about it first. All right, now say something out loud. Maybe like, what equations do you think you're going to use? All right, now try to work it out on your own. See if you can give me the polar coordinates of this point. Okay, here we go. So we've got the Cartesian coordinates and we want to get the polar coordinates. So the equations that we're going to use are r squared equals x squared plus y squared, because that's the Pythagorean identity, right? And then we can use that tangent of the angle is rise over run, because we are given x and y. We're given the rise and we're given the run, so we can find the angle theta. Let's start with the radius. So r squared equals x squared plus y squared, which is negative 2 squared plus 2 squared, which is going to be what? 4 plus 4, which is 8. So that means that r is equal to plus or minus the square root of 8, which is plus or minus 2 root 2. And remember, we do need to include the plus minus. So the general rule is anytime that you introduce a square root into a calculation, you must include a plus minus, because there are two possibilities at that point if you want to go backward through your calculations. You must include a plus minus, and then later on, you might be able to eliminate one of the solutions. That's the idea. So you must always use a plus minus and then later on get rid of one of the possibilities. We're going to do that in just a minute here. But remember, in the polar coordinate system, we can have a negative radius. So we're going to have to make a choice at some point. But before we decide which one of those we're going to choose, negative or positive, let's see if we can find an angle. So now we're going to use tangent of theta equals rise over run, as long as x is not 0. And this is going to be equal to 2 over negative 2, which is negative 1. So now, if you remember from, what was it, section 6.1 and 6.2, tangent of theta equals negative 1. What is an angle theta whose tangent is negative 1? What do you think? See if you can remember it. Think about it, and then say it out loud. All right, let's do it. So we're basically saying that the slope is negative 1. So I like to draw a little picture myself. It's going to look like this. You know what? Maybe I will pick the angle to be negative pi over 4. There we go. So that's an angle that works. Now, so that's what we're going to say. We're going to say theta is equal to negative pi over 4. Remember, you can choose any one of the angles that works here. You just have to make sure it makes sense in the context of your coordinate. So I chose the angle to be negative pi over 4, but where is this point, negative 2 comma 2, in Cartesian coordinates? On the little sketch that I drew down here, it's somewhere over here, right? This is negative 2 comma 2. So if I pick my angle to be negative pi over 4, I need to pick my radius to be the negative version, negative 2 root 2. So that way, even though I'm tipped down here, I'll be able to pass through the origin to get to that point. So altogether, I'm going to say that my point is given by negative 2 root 2, comma, negative pi over 4. And that works. Maybe you did it differently, right? That's one of the interesting things here. If you picked the positive angle, if you picked the angle 3 pi over 4, then you could equivalently write this point as 2 root 2, comma, 3 pi over 4. Those are the same point, just described in two different ways. But that's it. That's the conversion right there. All right, let's see if I did it. Okay, there's our radius. I did that part right. And then here's the angle. Okay, see, I said here are the two choices. And then I gave these two possibilities. Nice. And that's the idea. That's the idea. Right, so I hope that wasn't too bad. Now let's play. So you should go to the homework, try to do the homework for this section. You've got all the necessary skills, and we're going to use these polar coordinates in some really cool ways in the next section. Because I still haven't really answered the question like, why do we care about this? Why learn all this stuff? Why develop a different coordinate system? Any of that stuff. So we're going to talk about that next time. But before I ramble for too long, I'll leave you with that, and I'll see you next time.